Welcome to this explainer. I've spent well over a decade architecting backend systems, and I'm going to let you in on a little secret. Most of what we're taught about software development, it completely breaks down at scale. Today, we're not talking about writing basic CRUD apps. We are talking about survival in the cloud. We're going to tear down the illusions of perfect pipelines, expose the silent killers hiding in your database, and show you exactly how to build systems that don't just work, but actually withstand the absolute chaos of production traffic. It's the exact question every ambitious developer eventually asks. What actually separates a mid-level coder from a true senior engineer? Is it knowing a dozen design patterns, writing more complex algorithms? Nope, it's actually none of that. The real difference is a fundamental mindset shift in how systems are operated and maintained when the pressure is absolutely on. Okay, let's dive into this. Picture a junior developer joining a team. They immediately start adding features, APIs, validation layers. In their first year, they might proudly crank out 50,000 lines of code. Their contribution graph looks like a massive mountain range. But a senior developer? In their first month, they might actually delete 15,000 lines. They rip out entire microservices, drop bloated dependencies, consolidate functions. Their graph looks like a valley. And honestly, guess which one the company values more? This right here is what we call the code deletion paradox. See, every single line of code you write is a liability. For real, it's something that can break, it needs maintenance, it creates dependencies, and it adds to the cognitive load of every single developer who touches it after you. Senior engineers know human brains can only hold so much working memory, so they solve problems by removing barriers and retiring unused features, definitely not by building convoluted abstractions. All right, moving on to part 1, the lie of average latency. If you're just looking at standard monitoring dashboards to check your system's health, you're probably being lied to. So let's define the metric that actually matters, tail latency. We're talking about the latency experienced by the 99th or 99.9th percentile of your requests. Google engineers Jeff Dean and Luis Andrea Barroso famously pointed out a brutal truth about this. In large-scale systems, rare slow events, they aren't rare anymore. Because a single user action might trigger hundreds of downstream microservice requests, your high percentile latency will absolutely explode. And this brilliantly illustrates the exact problem we're talking about. Your average latency might look perfectly fine, maybe hovering right around 50 milliseconds. The dashboard is totally green. But at the 99th percentile, your endpoint is taking seconds to respond. That means for every 100 requests, one is timing out, failing, or causing a huge cascading bottleneck. At scale, that's literally thousands of users actively experiencing a completely broken system, all while your average metrics are telling you everything is perfectly healthy. So where is all that time actually going? Well, performance engineer Brendan Gregg proved that if you only profile your CPU, you are completely missing the big picture. The hidden killers here are off CPU delays. Your threads are just sitting there doing absolutely nothing because they're waiting on locks, blocking on disk I/O, completely frozen during JVM garbage collection pauses, or just waiting on slow downstream services. This hidden waiting time, it directly translates into user-facing latency. Which brings us to part 2, database migrations and meltdowns. Listen, if there's one place where junior mistakes can literally lock up an entire business, it is the database layer. Take the classic N+1 query problem. This happens when an initial query fetches N records, and then your application lazily fires off N additional queries to get the related data. So fetching 100 users might take 101 queries and cost you 808 milliseconds of network round trips. But by using eager loading, like a simple SQL join or an IAM clause, a senior engineer transforms that 808 millisecond nightmare into a single, highly optimized 15 millisecond breeze. That's a 54x performance improvement just by understanding how your ORM actually talks to your database. But what happens when you actually need to change the database schema itself? A junior engineer might just run an alter table command to drop a column. Let me tell you, on a table with 500 million rows, that naive command will lock the table for hours and cause a massive production outage. Senior engineers, they use the 3-phase migration pattern. First, expand. You add the new column using an online schema change tool. Second, migrate. You dual write your data to both columns and carefully reconcile them in the background. Finally, contract. Once everything is completely verified, you safely remove the old column. The result? 0 downtime, 0 locks. Next up, part 3, distributed systems always lie. So once your database is stable, you inevitably have to deal with the absolute chaos of microservices. To understand why network reliability is a dangerous myth, you really need to look at the Packelcy theorem. This actually builds on the famous CAP theorem. It essentially states that if a network partition happens, you have to brutally choose between availability and consistency. And else, meaning even when the network is perfectly healthy, you still have to choose between latency and consistency. You just can't have it all. You have to architect your system around these forced trade-offs based on what your specific business domain can actually tolerate. Let's make this real for a second. Ask yourself, what actually happens when a network blips right in the middle of a payment? The client sends a charge request, your server processes it perfectly, but then the network drops the success response back to the client. The client thinks it failed, so what do? They hit retry. If your system isn't designed for this exact failure, congratulations, you just double-charged your customer. Now, what's really interesting is how Stripe solves this exact nightmare. They enforce idempotent operations. Basically, every mutating request must include a unique idempotency key in the header. Stripe takes this key and stores it in a Redis cache with a 24-hour time to live. If you retry a request, Stripe checks that cache first. If the key exists, it validates that your request parameters are exactly identical, and then it just simply returns the cached response without processing the payment a second time. It's a remarkably simple architectural pattern, but it prevents millions of dollars in accidental duplicate charges. Moving right along to part 4, the reality of green pipelines. So you've written your resilient code, pushed it, and your CI/CD pipeline lets up bright green. Time to celebrate, right? Well, not exactly. A green pipeline is often a really dangerous illusion. Why? Because your tests are using mock data. Mocks are purely synthetic. They assume perfect schemas, ideal data shapes, and absolutely zero latency network conditions. But production data? Production data is messy. It has legacy shapes, weird serialization errors, and unpredictable network drops. If your pipeline is green, but production is failing, you've got a massive failure in mock-to-reality parity. Remember, unit tests are just theories. Production data is the ultimate judge. And that brings us to our final section, building for inevitable failure. Since we know for a fact that the network lies, databases bottleneck, and pipelines give false positives, how do the experts actually build systems? Well, they proactively built for inevitable failure by relying on chaos engineering. At hyperscale companies like Uber, a single request might trigger something crazy like 30,000 internal RPC calls. The combinatorial explosion of failure modes there is just impossible to test manually. So they use systems like drag and crawl to proactively inject failures. They're literally out there killing nodes, dropping packets, and maxing out CPUs on purpose, just to guarantee that a failure in a non-critical service, like recommendations, doesn't take down the core user flow of actually booking a ride. And to guarantee data integrity during all those failures, senior engineers rely heavily on the outbox pattern. Say you need to update your database and publish an event to Kafka. Doing those separately is just a split-brain disaster waiting to happen if one of them fails. Instead, you do this. Step 1, save your application state. Step 2, save the event into an outbox table inside that exact same database transaction. And step 3, a background worker reads that outbox table and safely pushes it to the message broker. By doing it this way, you achieve perfect consistency, even if your downstream services completely crash. So the absolutely crucial point of all this is simplicity beats sophistication. The best developers out there don't solve problems by adding endless layers of convoluted code, premature optimizations, or massive suites of synthetic tests. No, they solve problems by removing barriers, deleting dead code, decoupling state, and simply accepting the reality that hardware and networks will eventually fail. I really want you to take action on this today. Don't just close this explainer and go right back to mindless feature shipping. Pull up your system telemetry. Find your absolute slowest endpoint. I want you to stop looking at the average latency and look strictly at the P99 tail latency. Find out exactly what is happening off CPU. Seriously, apply this senior mindset to your own data right now. Because ultimately, it all comes down to this one question. Are you building just to ship features, or are you building to survive the chaos of production? Think about it. If you want to dive deeper into battle-tested backend architectures and really learn how to build systems that scale, make sure you subscribe to the channel. Thank you so much for joining me on this explainer, and I'll catch you in the next one.